Good afternoon, dear participants of the conference. I'm very happy to present my talk in front of you. My name is Skliarova. I work here in LNL, in the Laboratory of Superconductivity and Surface Treatment, headed by Professor Palmieri, that everybody knows here. I would like to talk to you today about a very critical topic for thin film deposition in general, and for niobium thin films for cavities particularly. It's porosity. Here, speaking about porosity, I would like to speak about the pinholes through the film. Porosity can be originated by different reasons. For example, dust particles from environment or metallic particles from the target or from the chamber can arrive to the substrate and be incorporated inside the film. And when the weak bonded particle is removed, it leaves a hole. Also, the surface defects can cause pinholes, like some protrusions can cause shadowing during deposition and after leave a hole, or some pitting after chemical treatment of the substrate can also be repeated in a coating. Porosity can be very detrimental for niobium sputtered cavities, because pinholes in superconducting niobium film can expose underlying normal conducting copper material, and in this case the surface resistance of the cavity is increasing, and correspondingly the Q factor of the cavity and accelerating film is going lower. So we have decided to investigate the porosity of niobium thin films corresponding to different deposition parameters, in order to find the approaches to deposit as less porous niobium films as possible. Probably the most known method for evaluation of porosity inside niobium films has been proposed by Amorosi, Benvenuti and collaborators. The idea is in measurement of the conductance of the gas through the film. For this, niobium film was deposited on disc copper substrates, and after, copper has been etched in the central part of the substrate. This copper washer with a niobium coating has been placed between two vacuum chambers. In one, helium gas has been inserted, and in another one, the through output of helium has been measured. This led to identify the surface area of the pores in the film. But this method is labor and time consuming, and it needs very accurate treatment of the film, because the film can be destroyed when you dissolve copper, when you place it inside the chamber, when you insert helium gas, etc. So we would like to propose here you much faster and easier method of porosity evaluation. We have deposited aluminum underlayer behind niobium in order to reveal the pore sites by visible products of corrosion. The test has been performed in hydrochloric acid solution. In this case, when acid penetrates through niobium pinholes, it's reacting fast with aluminum and producing hydrogen bubbles that are visible and detectable. We have used as a substrate quartz with aluminum sputtered on it in order to decrease the influence of the roughness of the substrate and minimize this source of the defects inside the film. We have evaluated the porosity of a film in a scale from 1 to 5, where 1 means the minimal amount of hydrogen bubbles and minimal porosity, and 5 means the maximum correspondingly. These conditions we will consider standard. We have deposited niobium by 2 inches planar magnetron of the second type of unbalancement. It means that in a planar magnetron, the external ring is magnetic ring is stronger than internal one, and you can see something like elongation of a plasma on the central axis of the magnetron towards the substrate. Standard placement of the samples was not exactly behind the plume and not far near the wall of the chamber, somewhere here. The standard configuration that we have used is magnetron up and sample downside. The distance between magnetron and sample holder has been kept standard. Argon has been used as sputtering gas. Niobium targets of high quality of RRR of 300 have been used. The base pressure was of order of 10 to minus 6 millibar, DC current 0.5 amperes. In standard conditions, we have not used the heating or cooling of the substrate, and the film thickness was around 1.5 micron. Here is the set of parameters that we are going to discuss. Is the position of the magnetron, pressure of argon gas, temperature of the substrate during deposition, film thickness, sample position according to the magnetron of unbalanced mode, and DC biased magnetron sputtering. When we have reversed the standard configuration when magnetron is up and the sample holder is down to the reverse one, we have obtained a decrease of porosity correspondingly. This is probably the most known method of decreased porosity everywhere. We have investigated the influence of pressure, depositing films at 3 to 10 to minus 2 millibar and 3 to 10 to minus 3 millibar with all other similar conditions, and we have not seen any difference in porosity of these thin films. We have deposited niobium thin films at different temperatures, starting from minus 100 degrees, obtained by cooling of the substrate with liquid nitrogen, to up to 500 degrees centigrade. The standard condition is here is something about 250 degrees without heating or cooling. And as you can see from here that when the substrate is heated, you see the decrease of porosity, probably because of some kind of regrowing of a film, because the atoms have a higher mobility when the process is when the substrate is heated. Sorry. We have compared the results that we have obtained on acid test of porosity with the direct measurements of porosity like optical profilometry and the scanning electron microscopy. The result of optical profilometry is the percentage of area covered by holes deeper than 0.5 micron. Here you can see the temperatures of deposition. In orange color you see the results of acid test, and in black one you see the optical profilometry results. And you can see from this picture that our decrease of porosity obtained by acid test is corresponding to decrease of porosity obtained by optical profilometry and also by scanning electron microscopy. The last sample, deposited at 800 degrees, was not possible to identify by our porosity measurements, and this is the limit of the test because of the melting temperature of aluminum. But nevertheless, the results shown by scanning electron microscopy and optical profilometry can be promising to decrease porosity even more. Here you can see the cross sections obtained by Skliarova electron microscope, and it can show you that in the case of films deposited at low temperatures, also the microporosity, the voids inside the film microstructure, can also influence the general porosity of the film. We have investigated the film thickness depositing films higher than 1.5 micron, and we have seen that the porosity decreased a lot, but even with a film of 10 microns, even the film with 10 microns of thickness is still porous. It means that there are probably macroparticles during deposition that are bigger than 10 microns. Sample position according to the magnetron of an unbalanced mode. In order to investigate it, we have placed sample exactly on axis, where we have a plasma bloom, and another sample far from axis near the wall of the chamber. And we have seen a very great difference in porosity, with a minimal porosity on axis and the maximal porosity outside. The reason of this low porosity can be regrowing of a film because of plasma etching. The difference of this increase probably can be the incident angle, that is smaller than 90 degrees in this case, and probably also the amount of particles arriving from the magnetron is higher in this position. And the scanning electron microscopy is proving this last idea, that the amount of particles and the size of the particles in the sample that is far from the center are much bigger and higher, and they are incorporated inside the film. DC biased magnetron sputtering has been found the most successful technique to decrease porosity of a film. We have investigated several bias voltages with a different pressure. Bias has been shown to influence more on porosity in a case of lower pressure, 10 to minus 3. And in any case is much lower than the standard samples. For one of the samples we have compared the data with the optical profilometry, and it has been found to be 0.1%. And also we have observed it with the scanning electron microscopy, and the film was found with minimal porosity, smooth and dense. So the winners of our race of techniques for films of minimal porosity is biased magnetron sputtering, deposition when the substrate is heated, and deposition of thick film. And of course, for whatever process, you can try to decrease porosity by increasing film thickness, placing substrate above magnetron if it's possible, and proper substrate preparation means cleaning, etching, etc. Avoiding, in a case of unbalanced magnetron, a position far out from axis, if it's possible, and use of clean room and vacuum cleaner to remove all metallic particles from the chamber. The work has been performed in collaboration with the Lima laboratory of the University of Roma. Thank you for your attention, and I will be happy to answer your questions.
Okay, questions for Anna? We have quite some time.
So, do you have an idea to apply your porosity test, your porosity test to our niobium copper sample? You should use another acid, right?
Okay, there is one idea. You can use copper sample, deposit first aluminum, and after deposit your niobium in a technique that you are going to check. And you can use the same test. In the case of copper, is a little bit more difficult because copper, exactly with this, it doesn't give you any bubbles, but it can give you color. There is a test, some called like a sponge test. You have to put acid wet with the paper or sponge wet with acid, and when it interacts with the copper, it is given a blue color. It will be like spots, but is less exact.
Yeah. Okay.
Just about this question, we choose the aluminum because the porosity is not so much related to the substrate, but to the growth of the film itself. And so to go with aluminum was faster, and we could have a lot of statistics. Moreover, Anna was doing also some work on liquid metal corrosion of across the porosity. What we saw is something like that, and she did also some tests on copper. But we were interested in thick films. Anna has grown, it was not such a presentation, also films of, what is the maximum, 250 microns on niobium?
In general?
You know, the maximum thickness that we got.
250, yeah.
250 microns of niobium by sputtering. Microns, not nanometers, microns. And it was also elastic. It was a nice film. And but still, the problem, and in that case, you forget the substrate when you go to 150 microns. So our interest was, to find, to see the, and you observe that porosity, even if you go to very high thickness, you still have. So the question is from where it comes out, the porosity, because the most trivial statement that Anna says is, I just tilt the magnetron and the substrate, I put the substrate up and I have less porosity. But our system is perfectly clean. Our target is 250 RRR, from where it comes out. So what we suspect is there are microparticles that from the plasma at a certain regime detach from the cathode and they go on the surface. And this is something that, in literature is not seen, and because Benvenuti and Chicciato did this paper on porosity, in which they
have investigated the influence of dust conditions and clean room conditions and the incidence.
You remember, 3 order of magnitude, they changed the passing into a clean room. But however, when you are in a vacuum system, nothing is more clean than a vacuum system, from where particles come, microparticles come, if not from the target. So this is another question. This does not depend on so much on the substrate.
Any other question for Anna? I have one. Have you tried to combine your most successful parameters? So, for example, to do a DC bias plus high temperature?
No, we have not combined. It's a dream, still.
I have a comment based on what you just said. It stimulates the following notion. When you did the experiment with a sample directly in line with the plume, and one that was on the side,
yes.
The one on the side was far more porous than the one that was directly in the plume. If there are such neutral microparticles, their proportionality would be much higher on the side than directly in the plume. And so to be consistent with your hypothesis.
I think so. We have seen that macroparticles that I have shown here. Here. And according to the ADX measurements, they are just niobium. It's.
But if I understand what you want to say is that not only there is the action of a plasma washing.
Yes.
But
also the amount of particles arriving to the other one. Yes. Absolutely agree.
Yeah. Thanks for the comment. I think this is also relevant when we want to code.
I was just curious if you had checked the substrate before to block for any substrate debris.
Give you mine.
I was just wondering if you had blocked for the substrate condition and mapping them to make sure there wasn't a particle on the substrate, some dirt or residue before you deposited. That was one. Two, have you balanced your magnetron and investigated the particle generation nature of your system? One thought is maybe you have your magnetron unbalanced too hard.
Wait. Let's start with the first one. The first one about, am I sure that the substrate was clean?
That's correct.
First, as I told, we have used quartz as the substrate. We have cleaned quartz before deposition. We have deposited aluminum on it. After, we have observed the aluminum deposited. The pieces in which we have seen holes inside aluminum with a simple light test, just closing and putting the quartz substrate on the light, you see the spots where we have holes. We have removed totally the pieces that were with holes. And after, we have used this aluminum sputtered on quartz in order to deposit niobium.
Have you investigated balancing your magnetron or changing to horizontal geometry to try to alleviate the particles? Because you're looking at vertical. Traditionally.
Okay, I understand what you mean.
Yeah.
We have used confocal sputtering, if you mean that. When the magnetron is tilted from the perpendicular to the substrate. We have used it for, I will show you now. We have used it in a configuration when we have had 3 tilted magnetrons with 120 degrees between them. And we have deposited in a place where the magnetrons are on focus, when the substrate in focus of 3 magnetrons and not in focus. And we have expected that this configuration should cover more all the holes because it should be more uniform. But what we have seen is that the porosity was still high. And we have seen not decreasing the amount of defects, but something like exaggerating of defects, and they became more round-shaped. So probably yes.
Sorry, this was done at what temperature?
This with floating near 200, 250, without heating or cooling.
The samples with floating temperature were not bad at all. I mean, it means maybe it's interesting to understand what floating it means.
What was the temperature of the flow? Yes, what means. I had a small detail question. When you talk about base pressure, 10 to minus 6 millibar, is this the pressure before?
Before deposition, yes.
So it's quite high.
Quite high, yes, I know. But the system is not devoted exactly
to.
to.
If you have porosity as well, it doesn't depend so much from. Yeah, that's the problem. And when you say it's cylindrical configuration, you have also the same thing.
Okay, are there any more questions for Anna? If not, we can
Thank you.
go to the next talk.